just a thought about the PN junctions, and then we come to know that if this is a PN not, n-type silicon minority carrier, equilibrium minority carrier concentration is PN not, and then we apply the bias to these junctions, then this concentration, equilibrium concentration will be enhanced to PN, new values. This is a space charge region edge, right? Space charge region. And this is the n-type silicon from the surface to the bulk. And this is going to show this profile, and we call this injections. Injection of minority carriers. And the low level injection means the majority carrier is not going to change much, but the minority carrier is going to be changed a lot. So we mainly concern on the minority carriers. This is a minority carrier profile after the bias, and then we know there should be a diffusion of these minority carriers to the bulk because of this concentration gradient, of course, to the fixed first law, and this diffusion can be expressed in terms of the current density, like round x round Pn, something like this, right? So continuity equation, says round Pn over round T should be this diffusion flux round x square fixed second law. Okay, this is a fixed second law, and then delta P over tau P. Okay, and here the delta P is Pn minus Pn naught. And at the steady state, this concentration change with respect to the time, it should be 0, and the general solution, is going to be delta P is K1 e to the minus x over LP plus K2 exponential minus plus x over LP. That is the general solution of this differential equation, where LP is diffusion length, and in terms of the diffusion coefficients, it can be expressed as tau P. Okay. With proper boundary conditions, should be applied to this general solution. Boundary conditions are Pn not, this is x equal to 0. Here is x equal to 0. And we call this as x. Okay. And that is P naught e to the phi a over phi t at x equal to xn. Okay. P n naught at x equal to infinity. that is the equilibrium concentration at this far end of right hand side. Okay? Then the particular solution is going to be P delta P is P n naught e to the VA, that is applied voltage, and the thermal voltage minus 1 e to the minus xn over LP. And since IP is minus QA dP round x round delta P, as we first discussed here, right? So we just apply this to the delta P here. IP is going to be QADP 1 over LP delta P, and that is QADP over LP delta P. And similarly, we can get for the current by the electrons dN over Ln delta N. Now the total current is the current contributed by the electrons and holes. So total current now is I total is IP x equal to xn plus In x equal to xp. Okay. Then the total current is going to be expressed with the equilibrium concentration of the minority carriers, and P naught over Ln e to the VA over VT minus 1. Okay, and this is constant values I naught. So we can say the current in this junction, PN junction, is going to be modulated by the applied voltages exponential terms. Okay. And also, I can be expressed in terms of Ni as I naught is going to be QA Ni square dP over N dLP plus dN over NA Ln. So far, just a review of the PN junction current we discussed the last time, okay? And today we're going to discuss about the MOS transistor operations. operation principles of MOS transistor. Well, the MOS transistor is going to look like this, and this is called the source and drains, which is heavily doped part of the silicon, and this is metal, so that it is going to be called MOS. This is the oxide, and this is a semiconductor, that's silicon. Now the gate is not, the metal is not used for the gate these days. We are using CVD polysilicon, but still we name this transistor as a MOS because we start out with the metals. Now, if you look into the vertical sections, we can have a kind of capacitor. We have a metal, and then have a semiconductor, silicon, and in between we have an insulator, SiO2, typically. That is the capacitor, right? So if you apply the voltages here, then it is a capacitor, actually. And depending on the gate voltage that we apply to the metal, we can attract the free carriers to the surface or repel the free carriers far from the surface. So we can have three different modes generally by manipulation of the gate voltages, and that is the surface accumulation and the surface depletion and inversion. That is the characteristic of MOS transistors, and that is related to the switching rather than amplifying functions of the transistors. Transistor actually has two main functions. One is the switching, and the other is the amplification. The MOS transistor is mainly for the switch, and for the amplification we usually use the bipolar transistors, which is going to be discussed after the MOS transistor. Now, if you apply let's suppose you have a N-type silicon as a substrate. If you apply the gate voltages plus, then you're going to collect electrons at the surface, so that here between the source and drain you can form channels, so that the surface is just conducting, right? But if you apply the gate voltages negative, then electrons is going to be repelled from the surface, so that we have a depletion region from the surface. And this depletion region, we're going to have XD thick, and this doped ions, dopants, is going to positively charged, deprived of the electrons, because it is repelled from the surface. So we do not have any free carriers to the certain distance from the surface, that is a depletion. Now if you apply the gate voltages more negatively, then the holes is going to be collected to the surface at this maximum depletion. And here we have conducting layers again. And that the conducting is going to be by the opposite minority carriers of this n-type silicon. And that is the inversion. Okay? So for all these, this is actually the capacitor, so that we can plot the capacitance of this system, MOS system, with respect to the gate voltages, positive and negative, and doubly negative, something like this, okay? And if you have an accumulation, then this, we have a capacitor corresponding to the oxide only, because we are conducting layers at the very surface, front of this silicon. But if you move to the negative side, then depletion occurs, so that we are going to have two capacitors connected in series. Okay, one is a capacitance due to the oxide thickness here, and then this depleted area also doesn't have any free carriers, so it works as an insulator, so that in series we have two depletion, two capacitance like this, and this capacitance is going to be modulated by the applied gate voltages. So it is going to decrease like this. And when it meets the strong negative gate voltages, then we are going to have inversion mode, something like this, so that this depletion layer capacitance is going to fixed to some values, and that is the capacitance minimum. And this capacitance minimum is the situation where we have two capacitance in series. One is oxide, and then the one is depletion, and this depletion capacitance is the minimum values, because the thickness is XD is fixed to the maximum depletion layer. So if you plot the capacitance of MOS transistors in vertical sections like this, then you're going to typically have something like this, okay? So now we have to discuss qualitatively what's going to happen on this depletion mode. This accumulation mode is a relatively simple thing. So we should talk about the depletion layer solution. This is going to be the topic to be discussed. Now, let's see. The Parsons equation says the potential, second derivative potential, is going to relate it to the charges in this manner. That is the Poisson's equations, right? And if you set this is the interface between the oxide and the silicon in MS transistor, and this is the x equal to 0, the surface, okay? And then the potential in a far bulk, we're going to have some potentials which is going to be phi B. It is going to be bulk potential. It is going to be called bulk potential, and then that is some equilibrium values. Okay, and this bulk potential phi B is corresponding to the doping concentration like this, right? That we have discussed. And when we approach it to the surface, okay, we're going to have some potentials which is corresponding to 0, and then it's going to change somehow, something like this. The potential is going to change something like this. And we want to get what this phi 0 is going to be if it maintains the Poisson's equations like this. That's what we try to calculate. Okay? And we're going to discuss about this, but we just put the designations here. The phi is a phi B prime, something like this. Okay? The reason why we put the prime here is that the reference voltages can be changed accordingly. So we just set phi a prime instead of a phi for the time being, and then we try to get phi prime 0, the surface potential. Okay. And let's say this is we have a p-type. Now set Q and A over silicon is going to be beta. Then electric field, which is integral of the charges, and that is going to be xd square 1 minus x over xd. All right? And if we make an integral of this once more, of this electric field, there we can get a potential phi x, and that is going to be 1 over 2 beta xd square. It's just a simple integrations, okay? 1 minus x over xd square. Plus phi b prime. And at surface, we want to know what the phi prime 0 here. At surface, you put the x equal to 0 in this equation, and and you end up with beta xt square plus phi b prime. And this is going to be called the surface potential. Right? So actually what you are saying is that you add this 2, then you end up with phi s, and that is designated as a phi s double prime. Okay? So this is a the phi s double prime is going to be let's leave it for a while. Phi s double prime, which is summation of phi 0 surface potential and phi b prime, right? Because the sign is, this is 0, the sign is different, so the summation means we should write something like this, and then this is going to be beta xt squared. And the strong inversion, we call the strong inversion. Strong inversion means we have a significant current path between source and drain. In other words, we form channels between source and drains, okay, by collecting considerable amount of free electrons or holes to the surface of the silicon. Okay, then that is going to be called strong inversion, and by definition, strong inversion means this potential is equal to the 2 phi b prime. Okay, and then we are going to have voltage along the y-axis. The voltage along the y-axis means we have gate here, and then this is the 0, and along this direction, so we call this is the x, and along this direction so it's going to be y. Okay, and here we have a source, and here we have a drain. So strong inversion says we have significant amount of free carriers at the surface, and how significant, how much, that is just corresponding to the bulk potentials. Okay? That is a strong inversion. In other words, this, the size of this is equal to the size of this phi b prime, and then we call that that is a strong inversion. Okay, if this is a p-type materials, we have this much holes in the bulk at the equilibrium condition, and by collecting the holes to the surface with the application of the gate voltages, and the amount of holes collected at the surface is equal to the amount of holes in the bulk, then we call that strong inversion. Okay? So in the equations we can write something like this for the strong inversion. All right? And we solve this equation with respect to the V xd solve for xd, then xd is going to be 2 over beta and phi s double prime, and 2 over beta minus 2 phi b prime plus vy. Now let's set QSD as the semiconductor depletion charge. Semiconductor depletion charge. That is in the inversion. If I set an inversion here, we apply the negative voltages, then we are going to have a depletion layers to certain distance xd, and that is modulated by the applied voltages here. Right? So we can calculate the xd with respect to the gate voltages, something like this, and semiconductor depletion charge means the charges that is going to be happen on this depletion layer. That is QSD. Okay? So, and that is nothing but A xd. That is the depletion length, and then that can be expressed as Na epsilon phi s double prime. Okay, and then that is epsilon 2 beta phi s double prime. And oxide capacitance is going to be expressed something like this for per unit area, and the potential drop due to the oxide, okay, is related to the charges and the capacitance, something like this. This is by definition, okay? And then this is going to be two Q Na epsilon over C ox times root phi s double prime. Okay, and this can be said alpha root 2 beta phi s double prime. Where now alpha is going to be set like this for the geometric vector. Okay, so now the total potential drop now is going to be the summation of these two potential drops. Okay, this phi s double prime is phi 0 prime plus phi b prime, right? And this is going to be alpha to beta root phi s double prime. That is related to the phi I and phi s double prime. So if you draw the oxide here, and then of course this is the metal, the gate, and this is the silicon, and the you can see that there is a phi s double prime, and it is going to decay like this, and this is actually phi b prime, okay? And we have straight line potential drop across this oxide, and then this is a phi I from here to here, that is phi I prime. When we just have the gate voltages, we later will define the threshold voltages, but this is when the gate voltage that we apply to the gate is equal to just the threshold voltages, just the strong inversion voltages. Okay. Now, what happens if you apply the voltage more than this to the gate? Then this thing is not going to be changed with the application of the gate voltages, but only thing is going to change is that this slope. If you apply more voltages, then we're going to have different slopes on this oxide, potential drops in the oxide. Okay, and then extra charges, QSD, is going to be contained in there, okay? That's what is going to happen. Now, flat band potential should be included all this. So that phi total got to be Vg Fb, and that is alpha root to beta phi s double prime plus phi s prime. So all these terms should support the flat band potentials. So gate voltages, now it's going to be a flat band potential plus alpha root to beta root phi s double prime plus phi s double prime. Okay, and then this is going to be equal to the phi flat band potential in QSD over Cox plus phi b phi s double prime. What it says is that the flat band potential plus potential drop in the oxide plus Okay, phi 0 plus phi b prime, which is phi s double prime, right? And this is nothing but phi t ln n a over ni, right? That is depending on the doping of the silicon substrate. Let me talk a little bit about the flat band potential here. Flat band, what is flat band potential? Flat band potential is nothing but the work function difference between metal and the semiconductor. Okay? And this work function of a semiconductor depends on the doping level, Nd or Na. So it is changing. The flat band potential is changing upon the doping. Now gate voltage minus flat band potential and since phi s double prime, as we discussed earlier, is beta xd square. It's going to be qna over cx xd plus qna over 2 epsilon xd square, and this is in our notation alpha beta xd plus 1/2 beta xd square. What we try to calculate is the capacitance. Okay. This is basically a capacitor, so the derivation of the capacitance is important. Vg minus Vfb is going to be beta 1/2 xd, and xd now is equal to minus alpha plus root alpha square 2 over beta Vg minus Vfb, and is equal to minus Cx plus epsilon square plus 2 Qna Vg minus Vfb. All right. So the capacitance now is QSD over dVg. Right? Capacitance of this system is going to look like this, and we know QSD is nothing but the charges in the depletion layer, and then the only the depletion layer width is going to be modulated by the gate voltages. So we want to see the derivation of that VG with respect to the gate voltages. So all we have to do is just make a derivation of this XD with respect to the VG to get capacitance. And then the capacitance now it should be upper scale plus 2 over beta Vg minus Vfb and then that is xd plus beta. Something like this. All right? So that is the first step to analyze the MOS transistors, the depletion layer solutions. And it has been extended to the strong inversion, and that the strong inversion naturally related to the gate threshold voltages of the system. Now, next week we're going to discuss about the drain current, which is mainly related to the switching properties of the MOS transistor, drain current, and we are also going to talk about the source threshold current. That's the characteristic of the switching properties of the materials of the MOS transistor, and body effect. And the velocity saturation. And after we discuss these basic properties of MOS transistors, we're going to discuss about the secondary terms like channel length, modulation by drain voltages. Okay, and 3/2 power equation. We're going to introduce over this 3/2 power at the drain current section, and we're going to discuss about the oxide breakdown. Also, we like a junction, p-n junctions. We have breakdown properties here, and the surface mobility consideration. In MOS transistors, free carriers are moving around along the surface, interface rather, between the oxide and the silicon. So the surface mobility term, consideration of the surface mobility is very important. And also we have to talk about the geometry effect, like a short channel or narrow or width channel, okay? How it is related to the threshold voltages mainly, okay? And the lead Chap phenomenon, which is also important in most high-level integrated circuits. And finally, we also going to talk about the scaling. What is this scaling law? To reduce the transistor size is very important, but we have to understand what's going to happen if you reduce the size in laterally or the vertically. How that related to the physics of the transistor functions and things like that. Okay. So we next week we start out with the drain current. Okay. Any questions? Okay. See you in the next week. We are not going to have a class on Wednesday.